Okay, so I had my equation up before about gravitational field strength equals gm over r squared. Now we're going to be looking at the proportionalities, so how the gravitational field strength is going to change as we change different parts of that equation. So the easiest part to see is the m, the big M up the top. I haven't got that up there, but the idea is if you double the mass of the object, the gravitational field strength around that object is going to double as well. There's a direct proportionality between the mass of the object and the gravitational field strength of the field that it produces. What we're mostly going to be looking at, and what my examples are about up here, is how the gravitational field strength changes as you move away from an object. So as you increase the distance between two objects, how does the gravitational field strength change the gravitational field strength produced by one object on the other object? And what we've got up here, we've got this little symbol in the middle. It means proportional to, so it means the gravitational field strength is proportional to 1 over r squared. I write it like that. It helps me eliminate all the other stuff that's up there, the big G, the big M. It helps me focus just on how the gravitational field strength is affected by the distance between the two objects. So that's just what this indicates to us. And we can see that the gravitational field strength varies as 1 on r squared. So it's an inverse squared relationship. As this gets bigger, the r value, the gravitational field strength is going to get smaller. This is what we expect based off that field diagram before. As we move away from an object, the gravitational field produced by that object is going to get weaker. So I've got my example up here. I'm saying that if g equals 9.8 at a distance of r, find g at 2r, 3r, and 10r. Now I've denoted g as g naught. That's going to be my starting value, and you're going to see why that's considered, why I'm using that kind of notation in a bit. You don't have to use that notation, it's just going to help things become a bit clearer. So at a distance of 2r, I'm going to write up g equals gm over 2r squared. This is my distance from the center. This is my equation from before, except instead of having r squared, I'm at a distance of 2r, so I'm going to write that in my denominator. Now, I put that all inside the brackets, and this is a crucial point. A lot of people would just write 2r squared. If you do that, you're not going to get out the correct answer, so just make sure whatever your distance is goes inside the brackets. Don't just write 2r squared and think that's it. Make sure you're putting in your 2r and then squaring that whole thing. So if I expand out these brackets, what I'm going to get is gm over 4r squared. And then what I'm going to do is, I'm going to pull out that factor of a quarter out the front, a quarter gm over r squared. And gm over r squared, that's the gravitational field strength at a distance r from the center of the object producing the gravitational field, which since it's 9.8, it's safe to assume it's the Earth in this situation. So because this is my value at a distance r for the gravitational field strength, I can say that that is going to be g naught. So I've got a quarter g naught, and I know what g naught is. The glare isn't killing this, is it? I think I'm just dodging it. A quarter of g naught, so I'm going to find that that's 9.8 divided by 4. And I know what that is off the top of my head, but some things I'm a bit anxious about pre-recording. I want it to flow a bit more naturally, and I feel like if I'm just banging things up out of nowhere, it'll speed things up, but now I'm just rambling, so whatever, I'll get back on track. So that's 2.45 newtons per kilogram. So it hasn't just gone down by a factor of 2, it hasn't become halved at double the distance. Because of that 1 on r squared law, if I double the distance, the gravitational field strength becomes a quarter of what it was. Camera's kind of jumping, whatever. So I just need to keep that in mind when I do these calculations, that if I double the distance, I'm not halving the gravitational field strength, I'm quartering it. And a similar relation here. I did this whole calculation, but once I get the hang of these, I can get through them a bit quicker. So at 3r, I know that my gravitational field strength is going to go down by a factor of 9, because 3 squared is 9. If I increase my distance by a factor of 3, I'm going to decrease my gravitational field strength by a factor of 9. So I know that whatever my gravitational field strength is, it's got to be a ninth of its value at r. So that's just going to be 9.8 divided by 9. And 9.8 divided by 9 is going to be 1.09 newtons per kilogram. Similar thing for the last one, same thing for the last one. I'm increasing my distance by a factor of 10. So my gravitational field strength is going to go down by a factor of 1 over 10 squared. This was 1 over 3 squared. I could have written that out, probably should have, but can't go back in life sometimes. So we've got 9.8 divided by 100 in this case. That's going to be 0.098 newtons per kilogram. So that inverse squared relationship is something you just got to get a bit of a handle on, that if you're increasing it by a factor of 5, the gravitational field strength goes down by a factor of 1 over 5 squared. Just keep that in mind. Now, the other thing we're looking at, and this is the end of chapter 1.2, is that we've done examples where, well, I've done examples, I don't know what you've done, where I've said the distance is this between the centers of the two objects, find the gravitational field strength at that location, at that distance from the center of the first objects. But this is something where it's a bit more involved. There's an extra step involved. The question says, an astronaut is 36,000 kilometers above the Earth's surface. What is the value of the gravitational field strength at this location? So I've got, well, I don't have the numbers here that I need to do this calculation, but I know them. Normally the question would provide you with those numbers, or sometimes you just do have to look them up in your textbook. You're not expected to memorize them for your exam, but you'll get a summary sheet that has numbers like the mass of the Earth on it. So you'll just need to be able to refer to that summary sheet, the formula sheet that is provided to you, in order to get those numbers. Sometimes the question won't tell you the mass of the Earth. You'll be expected to go to the formula sheet and actually find it there. So you're not expected to memorize this stuff. I memorize it because it's part of my job, but you're not expected to. Makes things quicker and easier if you do, but your call. So I calculate my gravitational field strength by just doing my big G, my gravitational constant, 6.67 times 10 to the negative 11, times the mass of the object that is producing the gravitational field, that is the Earth in this case, so the mass of the Earth. What I'm dividing by, though, is I've got 2 bits down the bottom. I've got my 36,000 kilometers, which I have converted into meters, added on an extra 3 zeros. I'm also adding on the distance to the center of the Earth from the surface. So it tells me that the astronaut's 36,000 kilometers above the Earth's surface, but remember it's the distance between the two objects that we use when we get our R value. So what I have to do is, maybe I'll draw this up, if it's 6.4 times 10 to the 6 meters to get from the center of the Earth to its surface, and then the astronaut is 36,000 kilometers above the surface, then I have to add these two values together like I've done here, the meters from above the surface and the meters that I've got to the center of the Earth. That's going to get me the distance between the center of the Earth and the astronaut above the Earth's surface. So just keep in mind that when you get a question like these, you need to consider what the reference point is. If you're told how far they are from the center of the Earth, easy stuff, that's your value for R. But if you're told how far they are above the surface of the Earth, you've got to also factor in and include the distance to the center of the Earth. Those two things added together are what are going to get you your R value for this question. Cool.